Well, welcome, guys. We are entering our last unit before the end of this semester, so you've made it almost halfway through the year. Let's make sure we finish this unit strong, that we work hard, and we look at the different ways that we can solve systems of equations. Now, let's just review really quickly what is an equation. An equation is a mathematical statement that has an equal sign. So, a system of equations is when we're looking for solutions of an equation of a set of equations. Most often, we're going to be talking about two sets of equations, and we're looking for the one answer that fits both of those equations. So, let's go ahead and look. We at some different methods. The first method that we're going to look at today is solving the system by graphing. So, our objectives for today are to be able to graph and use that to solve a system of equations. Now, a couple of things you might need for today. You might need a calculator. You might need something to take some notes on. And you might need some colored pencils or colored pens, just because sometimes using different colors is helpful with this. All right. So the first question says, what is the solution of the system of equations? And then they give us two equations. They say y is equal to negative 2x minus 4, and y is equal to 0.5x plus 6. So the first thing I'm going to do is I'm going to start by graphing this first equation. So because it's in slope-intercept form, y equals mx plus b, I begin at the b, which is at negative 4. So I go to my y-intercept of negative 4, and I plot a point. Then I look at the slope, and the slope is negative 2 in this case. I always like my slope to be a fraction, so I'm going to make it negative 2 over 1, which means from that point, negative 4, I'm going to go down 2 to the right 1. Now, I could also go up 2 to the left 1 in order to get my equation. My pen doesn't want to mark. There we go. So there's my line. Now, guys, just in case we're a little unclear, what this line means is any ordered pair on this line, any point that's on this line would be a solution to that first equation. So I have lots and lots of choices for my solution for my first equation. All right, so now I'm going to look at the second one. Now, the second one also isn't written in slope-intercept form. So I'm going to begin by graphing at the y-intercept, which happens to be at 6 this time. So 1, 2, 3, 4, 5, 6. And then its slope is 0.5. Now I'm going to rewrite that as a fraction, 1 over 2. So that tells me I'm going to rise 1, run 2, rise 1, or go down 1, and left 2. And I'm going to connect that one as well. Now, what this one says is any point that's on that line is now a solution to that second equation. But guys, when I'm solving a system of equations, I'm not looking for solutions for one equation or the other. I'm looking for the one point that satisfies both equations. And although I can't see that on my graph right now, because these are both lines and they continue on forever, I'm going to go ahead and extend this line up a little bit. And I'm going to see right here, there is a point that it happens to be on both lines. That point is the solution to my system because that point makes both of these statements true. So I'm going to take a look and count. First x, negative 1, 2, 3, 4, and then y, 1, 2, 3, 4. It looks like the point negative 4, 4 will be a solution to my system. Now, graphing is a great way to do this because we can see what we're doing. But sometimes if we're not really careful about our graphing, it can be hard to find our solution. So I always like to check my answer by plugging these values in. So again, this is the x and this is the y. And so I'm just going to check it in that first equation by saying, is it true that 4 is equal to negative 2 times negative 4 minus 4? All I did was plug the 4 in for y and the negative 4 in for x. So negative 2 times negative 4 would be 8, and 8 minus 4 is 4. So it is true that 4 equals 4. It works in this first equation. But it's not a solution to the system unless it works in both equations. So I'm going to check that one out too. And so I'm going to put the 4 in for the y and then say 0.5 times negative 4 and then plus 6. And so multiplying half of negative 4 would be negative 2. And negative 2 plus 6 is 4. So it also checks in that one. So I can say the solution to this system is at negative 4. Let's try another one. I'm going to give you a second to try this on your own. So if you've got some graph paper, go ahead and try it on your own. See how you do with getting a solution to this system using graphing. So in this case, I've graphed both of my lines. I started at negative 7 and went up 3 over 1. And then I started at negative 2 and went up 1 over 2. And I'm looking for the place where the two lines cross. In this case, it looks like I'm at 2, negative 1. And so again, I can check that out. Is it true that negative 1 is equal to 1/2 times 2 minus 2? Well, half of 2 is 1, and 1 minus 2 is in fact negative 1, so it looks like it checks out in the first one. And then in the second one, is it true that negative 1 is equal to 3 times 2 minus 7? So 3 times 2 is 6. 6 minus 7 is negative 1. Looks like it checks out in the second one. So my solution here is the point 2, negative 1. Let's try one more together. Go ahead and take a minute and see what you can come up with on this one. So this one starts at 10 and then rises to runs 1. Because I'm out of space, now I'm going to go down to left 1, down to left 1 to get a good accurate graph of that one. The second one begins at positive 1, and because it's negative, it's going down 1 to the right 4. Or I could go up 1 and to the left 4. And so this is my second one. I'm going to go ahead and extend that line a little bit, and it looks like it crosses right here at negative 4, 2. And so again, we can check that out and see if it works. 2 is equal to 2 times negative 4 plus 10. 2 times negative 4 is negative 8. Negative 8 plus 10 is in fact 2, so it looks like it works in that first equation. And then the second equation, I'm going to try, does 2 equal negative 1/4 times negative 4 plus 1? Negative 1/4 times negative 4 is a positive 1, and 1 plus 1 is 2. That looks like a good solution. So a couple things I've noticed is you have to be very accurate when you're graphing, and so be really careful. Use a straight edge if that's helpful to you. Count carefully. In order to find where they actually cross, we're going to have to be really careful and really accurate in our graphing. All right, so now we come to the next one. This one says, what is the solution to the system of equations? And use a graph to explain your answer. Well, one thing I noticed right away is this first equation is not written in slope-intercept form. So I can't use the same process that I've been using in order to graph. Well, I can. I'm just going to have to get that first equation in slope-intercept form. So I'm going to have to do some work ahead of time. So I'm going to start with the 15x plus 5y is equal to 25. And I'm going to work on getting that y by itself because that's what makes it in slope-intercept form. So to do that, I'm going to first move the 15x to the other side of the equation. That's my first step in getting y all by itself. So I end up with now 5y is equal to, and I can either write this as 25 minus 15x or negative 15x plus 25. It doesn't really matter. I'm just choosing to put the x first so that it's in slope-intercept form. All right, finally, I then need to divide each side by 5 in order to get that y all alone. And I end up with y is equal to, and then I have to divide every part by that 5. So negative 15 divided by 5 would be negative 3x, and 25 divided by 5 would be 5. All right, now it's ready for me to graph. So I'm going to begin at the positive 5. 1, 2, 3, 4, 5. And then my slope is negative 3. I can write that as negative 3 over 1. So that says go down 3 and to the right 1. And I have my graph. All right, now I'm ready to graph the second equation, and it is almost in slope-intercept form. Y is by itself. It's just written backwards. And so I need to look at this one and I need to determine where would the y-intercept be. So in this case, the y-intercept is also at 5, and the slope is also down 3 over 1. So what you notice here is that I have graphed one line right on top of the other line. These are both the same equation. And so what that tells me is the solution to the system will be every single point that's on this line because they overlap. So every point that's a solution to one line is also a solution to the other line. Therefore, this is what we call a many solutions type of problem. All right, next example. Same kind of situation here. They want us to use graphing to solve. However, these aren't in slope-intercept form, so we're going to have to do some work to get them in slope-intercept form. So starting with the first equation, y minus 2x is equal to 6. Our goal is to get y by itself. So the term, the minus 2x, is on the same side as the y. So I'm going to move that whole term to the other side by adding 2x. In doing so, I end up with y is equal to 2x plus 6. And I don't have to do any division here. This is now in slope-intercept form. So I'm going to come up here to the 6, 1, 2, 3, 4, 5, 6. And then I'm going to plot my slope, which says rise 2, run 1, up 2 over 1. And I've got my line drawn right there. All right, second equation, also not in slope-intercept form, so I'm going to work on getting that one ready to go. That means I'm working on getting y by itself, so I'm going to start by moving the term negative 4x to the other side by adding 4x to each side. I can't combine the 8 and the 4x because one of those terms has an x, the other does not. So that's going to become a 4x plus 8 is equal to 2y. All right, finally, to get that y by itself, I'm going to divide each side by 2, and I end up with y is equal to, remember, we have to divide each part. So 4 divided by 2 would be 2x, and 8 divided by 2 would be 4. So this one tells me I'm going to begin at the y-intercept of 4, so 1, 2, 3, 4. And then it says I'm going to follow a slope of 2, which means up 2 to the right 1. Up 2, oops, up 2 to the right 1. Up 2 to the right 1. And so this one looks like this. So guys, when I look at these two lines, I notice that these two lines don't cross. Even if I extend these lines out a long way, they're not going to cross. And something I notice about their equations is they have the same slope. Remembering back a couple of units, same slope means the lines are parallel. And if lines are parallel, that means they'll never cross. If they never cross, they don't have a solution. And so in this case, this would be a system that has no solution because they'll never intersect and cross. All right, finally, we're going to look at a word problem that we could use systems to help us solve. It says Monisha and Holly have 14 more days to finish reading the same novel for class. Monisha has made a plan to read 9 pages each day, while Holly plans to read 20 pages each day. Assuming Holly and Monisha both maintain their reading plan, when will Holly catch up with Monisha? who will finish reading the novel first. Okay, so let's take a look at what we see. Right now, we see that Monisha is on page 96 already. So when I go to write Monisha's equation, I'm going to say Monisha is going to read, it tells me she's going to read 9 pages each day. Since that's the thing she's doing over and over again, that would be considered my slope. And then 96 would be considered my y-intercept because that's where she's beginning her program. Holly, on the other hand, is beginning her work at page 6. So her y-intercept would be over here at page 6. While she is going to read 20 pages each day, so that would be considered her slope. So Holly is reading 20x plus 6, and Monisha is reading at an equation of 9x plus 96. So the question says, when will Holly catch up with Monisha? What that's asking is, when are they going to meet up? Now, to finish this one up, I'm going to use a program called Desmos because this is one that graphing would not be super fun to use. And so I'm going to plug in my 2 equations. So y is equal to, Monisha's was, let's come back to her equation, was 9x plus 96, 9x plus 96. And then I'm going to put in Holly's equation, and Holly's equation was 20x plus 6. So y equals 20x plus 6. Now, if you'll notice on our equation or on our graph here, we can't really see too much. So I'm going to go ahead and zoom out just a little bit so that we can see. And we see right up here, there is a point where they do intersect. It looks like 8.182 and 169. And so what that tells me is at this point, at about day 8, or somewhere around day 8, they're going to meet on page 169, 170, somewhere in there. Then when we look at these 2 equations, we can see that Holly, who is the blue line here, at that point, up until that point, she has read fewer pages than Monisha. However, at that point, she now overtakes and begins reading more, or is further in the book than Holly or than Monisha is. All right. Question 3 says, suppose Monisha reads 10 pages each day instead. How would that change her equation? Would the 96 change or would the 9 change? Will this change the length of time it'll take for them to meet up? Again, we can explore this by going to that desmos.com and changing those equations and seeing how it changes the process. We can answer any of these questions from looking at that graph, but I just wanted you to explore a little bit and know that that program, desmos.com, it's a graphing calculator. We've used it a few times in class, but that's a program that you can help when you have a graph that's kind of big like this one. It would be hard for me to graph accurately 96 and up 9 over 1, or positive 6 and up 20 over 1. And so that program allows me to do that in a little bit more. All right, so what you're going to do now is you're going to work on Pearson, lesson 4.1. We're going to do some practicing with graphing systems of equations. Just as a review, systems are 2 or more equations that we're solving at the same time. We're looking for the one solution that fits both equations. And so that happens where the 2 lines intersect. There are 2 special cases. Sometimes when we graph, we get one line exactly on top of another one. That's a mini solutions because every point on one line also is a solution for every point on the other line. And the second idea there is when we get 2 lines that will never intersect, they're parallel, and that will give me no solutions. Guys, I hope that that this makes sense. And if you've got any questions, make sure you're giving Mr. Jordan or myself a call so that we can get that figured out. Guys, this unit, we're going to learn 3 different ways to solve systems, and it's really important that you understand each one individually before we move on to the next one. so that you can decide for yourself which one you think is most beneficial to you. I hope that helps, and I hope you have a great rest of your day.